بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone. Today inshallah we're going to be continuing on Lyapunov's theory. Again, as usual, start with a recap of what we covered so far. We're still focusing on systems of this form, okay? State space models, x dot is equal f of x plus g of x u. For now, we're forgetting about the u part because we're only interested in studying the stability of systems of this form. X dot is equal to f of x, and again, we either chose the control law and we're studying the stability of the closed loop system, or we're interested in studying the stability of the system without any control. There is a slight modification, again, in what I said and also in the slide of last time. I'm going to find in the previous lecture, it was written that the stability of the systems of the form. And again, I'm going to stress on the fact that there is no such thing as a stability of a nonlinear system. Why is that? Because it has multiple equilibrium points, exactly. So you need to study the stability of each equilibrium point separately from the other. Linear systems are different because it has only one equilibrium point, which is the origin. So if you study the equilibrium, the stability of the whole system, it's equivalent to studying this origin equilibrium. The first method that we said, okay, it's the easiest one that you can do. It's very straightforward, which is let's do a first order Taylor expansion around these equilibrium points. We're going to get a linear system that's equivalent to the nonlinear system. The Z now is different from the X. It's just a perturbation from this equilibrium point. And the stability conditions using Lyapunov's indirect method, or just the linearization method, is that you compute the eigenvalues of this Jacobian matrix that's evaluated at the equilibrium points. Just leave this open. Okay. There will be just more people coming, so. And if you have at least one of the eigenvalues is positive, you can immediately conclude the instability of the equilibrium point of the nonlinear system. If you have all of them to be negative, you can conclude that there is a very small region that if you start near this equilibrium point, you will always converge to it. And by the way, this can be very small. So we don't have any guarantee on how big or small this is. This usually region where you start in and you conclude, does anyone, and you converge to the equilibrium point, does anyone know what that's called usually in system theory? It's called the domain of attraction. So that's just the standard terminology for it. It's called the domain of attraction. And there are methods if you want to quantify for a given nonlinear system how to do that. We're not going to be covering that. If you have eigenvalues that are zero, if you don't have any positive real eigenvalues, and all the remaining ones have zero, they are on the imaginary axis, then this means that you cannot conclude. Okay? Lyapunov's direct method will fail in this case. Then we looked at Lyapunov's direct method, which looks not only at the linearization, but it takes the whole nonlinear system as is. So x dot is equal to f of x. And we're going to be studying one of these equilibrium points. We'll be doing it separately for each one. If you can find, and this is how the theorem states, if you can find such a function, which is called the Lyapunov function, that has zero at the origin, or sorry, zero at the equilibrium point, so the value is equal to zero, and everywhere around this equilibrium point it's increasing, and also the rate of change of this function, which is the v dot, along the trajectories of the system, so along x dot is equal to f of x, you can show that it's negative semi-definite, then you can guarantee stability of the equilibrium point. If you can, in addition to the first two conditions, you can also show for some Lyapunov function negative definiteness, so not negative semi-definiteness, negative definiteness of the rate of change of the v, then you can show it's asymptotically stable. If you can guarantee also that this applies for everywhere in the state space, you can guarantee global asymptotic stability. Okay. And we looked at the two examples, one which is the pendulum. This was the pendulum state space model, again written with some constants. We just replaced all of the mass, the damping coefficient, the length, and also on, and we put two positive constants. We had two equilibrium points, one which is the downward position, one which is the upward position. Then we looked at Lyapunov's indirect method. We took the Jacobian of this dynamical system, evaluated it at the first equilibrium point. We got this 2x2 matrix. We did the same for the second equilibrium point. We got this other equilibrium. We got this other linear system, 2x2 matrix. And then I showed you last time that for all positive values of C1 and C2, you can show that all of the eigenvalues are always negative. While for the second system, you can show that the second one, no matter what C1 and C2 you choose, it will always be positive, so the real part of this second eigenvalue. So you can conclude that the second one is unstable. We guarantee that the first one is locally asymptotically stable. Can we prove that the first one is globally asymptotically stable? Why? Exactly, you have another equilibrium point anyhow. If you have only two equilibrium points, one of them is unstable, and the other one, you know it's locally asymptotically stable. What does that imply?
It is not globally stable. It is not starting at this equilibrium point. If you always return to the
Exactly. If you don't have the initial condition of the nonlinear system starting precisely at pi and 0 with this initial condition, this means that you will always go away from this equilibrium point, and then you will go to that equilibrium point. And this also makes sense. If you start a little bit to the side from the upward position, the gravity will take you and make you, after some time, converge and stop at the lower equilibrium point. So in this case, we say that this equilibrium point is, we call it, it's almost globally asymptotically stable. It's not theoretically globally asymptotically stable, because there is some point in the state space where we cannot converge to this equilibrium point from. However, this is, if we exclude this equilibrium point, then we can converge to it. So this is known as almost global asymptotic stability. Then we looked at Lyapunov's direct method. We guessed this Lyapunov function, and we said that this is a very natural Lyapunov function. Why is that? This is a very natural Lyapunov function to guess. Why is it? It is an energy. It's not just an energy, like it is the actual energy of the system. So this is the kinetic energy of the system, and this is the potential energy of the pendulum. And then we derived last time, and I showed you very quickly, that Vdot of x is equal to minus, it's a quadratic function of x squared, x2, it's a quadratic function of x2 only, and this means it's negative semi-dev. And I'm going to comment on that. We're going to look at more details today. How can we say that a function is positive or negative or semi-definite and so on? If you just plot how this function v of x looks like, because again, it has some trigonometry in it and it's not trivial. Why is it positive always? You can just show that it is truly always positive away from the origin. Lyapunov's indirect method, just as a note, we did it for the two equilibrium points. Lyapunov's direct method, we will do it only for the locally asymptotically stable one. What happens if we try to choose a Lyapunov function for the second equilibrium point? What if we say, let's try to show the stability of the second equilibrium point using Lyapunov's direct method? What problem will you face? So if I tell you, try to guess a Lyapunov function that you can show that the equilibrium point, which is the second one, the upward position, is unstable, what will you do? What will happen? What? No, I'm saying about using Lyapunov's direct method.
You cannot assume for potential energy on that position the same. Because it's unstable, right?
It is unstable. What does that imply? We already know it's unstable, but what does that mean? No? Exactly. We will never find any Lyapunov function that we can prove the stability with. So keep on trying as much as you want. You will never find this Lyapunov function. It doesn't exist. And this is the problem of Lyapunov's method. It doesn't tell you how you can find the Lyapunov function. It tells you if you find a function that you already know that you can prove these conditions and it has the v dot equal to that, then you can prove the stability, but not the other way around. It doesn't tell you what the v is. Okay, and of course, if we always choose the energy, we will never get that v dot is negative semi-definite or negative definite at that equilibrium point. We can't even show. Oh, that's it. Okay, I'm just gonna stop.
But if you go back to the previous slide,
Yeah.
of the A2 phase, you were just telling that it is like near globally asymptotically stable.
No, what I mentioned about the globally asymptotically stable was X1, not X2. Okay.
So, Professor, is there any way that we can mathematically prove that it does not exist?
That's a very hard question. I don't know. I don't know the answer.
We cannot claim from the direct method that it is unstable.
Exactly. The direct method doesn't say that. It tells you if you can find the Lyapunov function out of the infinite possible Lyapunov functions, then you can show it. But if your choice of Lyapunov function doesn't conclude stability asymptotic or global asymptotic stability, what does that mean? No. It means try another function. It means try another function. Doesn't mean it's unstable. Okay. You cannot conclude anything if you don't satisfy this condition. Okay. It means that try another function. That's it.
So the only way we can actually prove that it's unstable is to go by the indirect method.
This is the easiest way. There are also more fancy ways that you can try to prove instability. And theoretically, if you can find the Lyapunov function where v is 0 at this point, and v is positive around, so it's positive definite, and you can show that v dot is also positive definite, you can conclude by Lyapunov's theory that it's unstable. However, it's very hard to find this Lyapunov function that it's positive and also its v dot is positive. Okay, it doesn't make sense. Okay, it's very hard. So it's not even used in practice. Okay, that's just theoretically. The other example we looked at was the satellite. We had this part of the kinematic equation and the whole the kinematic and dynamic equation for a rotating rigid body. So there was the r dot equal to r some multiplied by omega tilde. And we said that the system, the second momentum equation doesn't depend on r. So we just removed it. And we looked at omega dot equal to this gyroscopic effects. We don't have any torques. We just forget about the torques for now. And we wrote it in this form, again, by expanding it and assume that omega 1 and omega 2 and omega 3 are around the principal axes. So J is diagonal. And then we just did some simplifications to show that we have this nonlinear system in the end where C1 and C3 are positive and C2 was negative. We showed that we have 4 equilibrium points given by these values there. The first one is that the body is not moving. It's just stationary. The second one is that it's rotating around the first axis. The second one is rotating around the second axis. The third one is rotating around the fourth equilibrium point is rotating around the third axis. Then we used only Lyapunov's indirect method. We got we evaluated the Jacobian at the 4 equilibrium points. We showed that this has 3 zero eigenvalues. We cannot say anything about it. This has 1 zero eigenvalue. This has 1 zero eigenvalue, while the remaining other 2 eigenvalues are complex conjugate and on the imaginary. So all 3 real parts of these eigenvalues were on the imaginary part. This was the only one that we showed actually it has 1 positive eigenvalue, which means that we can conclude it is unstable. Okay, and I did this nice. I don't know if you found it nice or not. I don't know if you had the time to look at it in slow motion, but again, can find different. Maybe there are better people did it on YouTube. Now let's dive in more into positive definiteness. Last time it was not clear to some of you, or maybe because some of you saw it for the first time. What is the positive definite function? Okay, and how can we in practice show it really that a given function is positive definite or not? So a positive definite function locally, okay, so we say that a function psi, that it's a function from a manifold X, which in our case is the state space, to R is locally positive definite about some point, okay, X star, if we evaluate that function on that point and we get 0, and there exists some neighborhood. So there is some sort of small region around this point that includes the point, such that the function is positive while you are in that region, excluding, of course, the point which is that has 0. Okay. If you have a function that satisfies this abstract notion, then you say it's a locally positive definite function. Okay. We close the door now. And again, this is the definition of a locally positive definite function. We can refine the definition a little bit to define semi-definite function, globally positive definite functions, and negative definite functions or negative semi-definite functions, locally, of course. So if this function is in this region is greater than or equal 0, so which means that not only that this point x star that we're interested in is the only one that has 0, but also there are other points around it that have 0 as well, then we say that it's positive semi-definite. If this function is always positive for all values in the state space, not just in some region, we say it's globally positive definite. If it's, again, if you have everything inverted multiplied by -1, then we call this negative definite, negative semi-definite, locally or globally, and so on. Okay, everything holds by just inverting the sign. So this is the definition of what a positive definite function is, or its counterparts. There is a very important implication of this behavior. Okay, again, analytically, we're not going to be plotting any functions because, again, we want to look at it analytically. We might have infinite dimensional functions, or like it's functions of some functions of functions. You can have that. You can have functions of k-dimensional vectors or functions of k-dimensional manifolds. So just let's try to think of it abstractly, not just plotting it. If x star is a strict local minimum of psi, and the function increases in every direction from x star within this neighborhood, then we say that psi is a locally positive definite function. Okay. It means that if you look at it, if you zoom into this function, again, take the 1D example, you're going to find that it looks like a bowl, right? Just like a parabola locally. If you look at it in 2D, then you have like a parabola on both sides. You have a paraboloid that goes in 2 dimensions. And again, you can generalize this to n dimensions. There is a classical result of multivariable calculus, you might recall or not, that if we have that psi is a differentiable function, and x star is a local minimum, then the gradient must vanish, right? If you have this, like take the 1D example, if you have a paraboloid, and you say that x star I have function is equal to 0, and everywhere else it's increasing. What does that mean? It means that this x star is a local minimum of this function. And what does a local minimum function, what does a local minimum point mean? It means that if you take the gradient of this function and generalize it to the Jacobian if you have multiple dimensions, if you take the Jacobian of this function and evaluate it at this point, you should get 0, right? Is this familiar to everyone? Okay, from calculus. Points that satisfy both the condition that when you evaluate it at the function is equal to 0, and you evaluate the gradient or the Jacobian in general, and you find it is equal to 0, we call it a critical 0 of the function. Okay, so far so good. Okay, so hopefully there's nothing new, just a refresh of what you already know. Now let's look at something completely different, something you probably also have been exposed to before, which is positive definite matrices. Who has heard this term before? Positive definite matrix. Okay, makes sense. You definitely heard about it. If I give you a symmetric matrix, okay, a symmetric matrix A, it's Rn by n. We say that this matrix is positive definite if you have that this function which is made out of A, which is x transpose Ax, is always greater than 0 for all x except for the origin. Okay, so if you take any vector that's not the origin, that's not the 0 vector, and you multiply x transpose by Ax, you find that this value is always greater than 0. And again, you can refine this definition. If you have greater than or equal to 0, this means that's positive semi-definite. If you have that's always less than 0, it's negative definite. If you have it's less than or equal to 0, then you call it negative semi-definite. Okay, this should also be familiar from before. Now, what is the nice thing about positive definite matrices or that are symmetric is that you can conclude without that it will satisfy this property by just looking at the eigenvalues of this matrix. Okay, and this is usually the notation that is used when we want to say that a matrix is positive definite, positive semi-definite, negative definite, and negative semi-definite. Okay, you just look at the eigenvalues. take the matrix, calculate the eigenvalues in your usual way. If you find all eigenvalues are positive, we say this is positive definite. All eigenvalues are negative, we say it's negative definite. Some eigenvalues are positive and some are zero, which means that they are always non-negative. Then we say that it's positive semi-definite, and vice versa, we say it's negative semi-definite. So far, so good. How is this positive definite matrices useful, or this check useful for positive definites of functions? And again, why are we talking about positive definite functions? Because we want to use that in Lyapunov theory, so don't get lost in that. Now let's look at Rn for simplicity now. So let's look at the states, the manifold that we're talking about is Rn, and we have a function that goes from Rn to R. We want to check whether it's positive definite or not. Okay, it's a multivariable function, it's nonlinear. Okay, and we want to see whether around some point it is positive definite or not. Then what the easiest thing that you can do is you can expand this as a Taylor series of order 2. You get the first one, which is V of x star. Then you have the Jacobian evaluated at x star multiplied by x minus x star. Usually you're going to find this notation with a transpose. Okay, we might see it with the transpose, but I don't use that notation. Go back to when we defined the gradient, we said that the gradient or the differential of the function is actually a covector. Go back to one of the previous lectures, and this means that we're going to be writing it as a row vector. Then we can multiply this row vector by the matrix directly. So there is no transposes. So this is the Jacobian multiplied by x minus x star, and then you have here another n by n matrix, which is called the Hessian of the function v. And you multiply by x minus x transpose x minus x on both sides. Okay, so just to have a quadratic function. And also you have higher order terms, but we're going to only looking at the Taylor series of order 2, and all of the higher order terms we're going to be neglected. This HV is an n by n matrix called the Hessian. Okay, who is the first time to hear about this Hessian? Who hears it for the first time? Everyone knows about the Hessian? Okay, very good. Then you know that it simply has all of the second order derivatives. The Jacobian had all first order derivatives. The Hessian has all second order derivatives. Each one of these functions is actually another map from Rn to R. Okay, so each entry of the Hessian matrix, each one of these n by n matrix, n squared entries is a function that takes Rn to R. Why is all of this important? Is because if we're again from the result, the simple result I showed you earlier, if we want to check whether v of x is a positive definite around some point, then we know that v of x star is 0. We know that the Jacobian of x star is also 0 because it's a critical 0. Then in the end we can approximate this function, no matter how nonlinear it is, no matter how scary it looks like, simply by the Hessian. What does this remind you of? What does this look like? Exactly the same structure or the same form that we use to talk about the positive definiteness of the Hessian itself as a matrix. So in the end, if you want to show that some function is positive definite around some x star, around some point, which in this case is a critical 0, it's a critical 0 of the function, then you can only check for the positive definiteness or the definiteness of the Hessian. And simply, how do we check the definiteness of this matrix? By simply the eigenvalues. So again, in conclusion, take the function no matter how scary it looks like. Take the second partial derivatives of it with respect to all of the variables that you have, and then look at this function. Look at this matrix. Compute its eigenvalues, and if you find all of the eigenvalues positive, what does that mean for the function? No. Locally positive definite, absolutely, exactly. It's locally positive definite. Don't forget about this approximation. We're looking locally around the function. We also have higher order terms, and these higher order terms might make this function away from the equilibrium, from this critical 0, behave differently. That's why it's only locally, okay, this behavior. So this equation, okay, and this result, okay, means that positive definiteness, positive semi-definiteness, negative definiteness, negative semi-definiteness, I can always evaluate it by looking at the Hessian of this function. Yes, Mark. That's right.
We use multiple table extension. So I know the state as equilibrium, and for example, x I interested in is far about.
Yep.
And get x between from this equilibrium, and this x between is x star relative to the x I interested.
Yeah. Okay, so the question, let's start with the first question first. When I'm evaluating this and I want to look at faraway points, right? So faraway points will not satisfy this equation. I'm gonna get some error because of the higher order terms. Will that affect any decisions I make with this Lyapunov function? The answer is no, because I want to only check whether the reason why we're doing all of this is that we want to have some function v, and I want to check its local positive definiteness around x star. I don't care about anything else. If I can show that this function v is locally positive definite around this origin, then I can use it as what? As a Lyapunov function, right? So Lyapunov functions, I only need to find the locally positive definite function. I don't need to find it globally. So I don't care what happens away from this equilibrium point. I want to study the stability of an equilibrium point, and I have a function that I guessed it, and I want to check whether it's positive definite or not. Then I calculate v dot, and I want to look at v dot in a local region around the v, okay, whether it's negative definite or negative semi-definite or not. So I'm not interested that away from it. Okay, so for our purposes of using it for Lyapunov theory, this is just enough. Okay, combining it with other tailored expansions is out of the question. We don't need it here. Okay? Yes.
But locally, how long is it, the range?
Very good question. This doesn't say anything. Locally means you're small in a neighborhood. You don't have any way to, again, by this equation, I can quantify it, okay? But other than that, that's it. So, and we're also not, and now you're asking about this idea of domain of attraction. So if I show that an equilibrium point is locally asymptotically stable, how big is this region where I can start near it and I can converge to it? This is, you're going to talk about the domain of attraction. See? Again, and so if you look at some methods that try to quantify this domain of attraction, you're going to find that they're going to be trying to, again, use or try to estimate this region. Okay, and these methods, they usually estimate the region, but they don't calculate it precisely. And this estimate can be very conservative, right? So in the state space, you can have an actual very big domain of attraction, but the method might tell you that, okay, I'm in this very small region. Depends on the method you're going to be using. Okay. For our purposes, Lyapunov theory doesn't need all of that. It just needs, again, if you go back, it tells you find a positive definite function, and now we have a way to assess whether we have a locally positive definite function or not. And then we can check the negative semi-definiteness, whether locally or not, we don't care also. It will work in both cases. Okay.
So from what we have shown in the previous slides, the V, the V is like a matrix. No, not the V.
No.
The Jacobian of the V is a matrix.
That's right. No. For Rn, it's a matrix. If you want to look at, so now you're asking the question of, what if Rn, we don't have Rn, we have a manifold here, right? The Jacobian and the Hessian will be matrices of the same form, but only in a local chart. Okay, so if you look at them in a chart, you're going to have the Hessian look like this and the Jacobian looking like that. Okay, but what are they geometrically? Again, we can give them a fancy name, and we're actually going to do something. I'm going to give you a glimpse of that in the next part immediately. Okay. Any more questions? Okay. Now to the geometric interpretation of Vdot. So now if I give you some V or some V dot, you know how to, again, as a function of Rn, you know how to check whether it's positive definite or not. Let me just go back a little bit to what we discussed last time here. Now, by looking at this V dot, can you tell me from all what we discussed whether it is positive, whether it's clear now it's negative definite or not? It's negative semi-definite. How can you show that? Let me do this calculation very quickly. Oh. So this function v, so the function v dot, which is of x, and x here was equal to x1, x2, right? Which, to remind you, was theta and theta dot in the pendulum example. We calculated v dot to be equal to minus half c2 x2 squared. So x2 squared. Okay. In the last lecture, the c2 we shows it to be 1. If you put them to be symbolically, you're gonna get it to be here. Written as a quadratic form. What does this look like? It looks like this. It looks like half x1, x2 multiplied by matrix and then multiplied by x1 and x2. We have here c2. We have here 0, 0, and 0. Right? So this is equal to minus half x transpose. Let's call this matrix in between C and then X. Okay. Now, the only thing that, first of all, this is negative, and we need to check the definiteness of this C. Let's calculate the eigenvalues. The eigenvalues of this is trivial. What are they? They are 0 and C2. So these are the eigenvalues. So I have one eigenvalue, which is 0, and I have another eigenvalue, which is C2. Do you remember what C2, C1 and C2 here? They were always positive numbers for the example of the pendulum. And no, C2, you're confusing the pendulum example with the satellite example. So the satellite we had three constant, and the pendulum had only 2. So 0 and C2 are the eigenvalues of this matrix. So I have an eigenvalue that is 0, which means that C, what type of matrix is C? It's positive semi-definite. Okay, and this was the notation that we had. So if C is positive semi-definite, then by the minus sign, it becomes what? It becomes, then V dot is negative semi-definite. And now it's clear. Okay. And you also remember what I told you last time. But by looking at it, we said that it doesn't depend on x1. And if it doesn't depend on x1 and you write it as a quadratic form, you're going to find that this is always 0 term. And if you have something as a 0 on the diagonal, it means that the eigenvalue that corresponds to it will always be 0. That's why if one of the variable, if you have a multivariable function, v of x1 and x2 and x3 and so on, and one of the variables is missing, this is a very easy check to say whether it's positive definite or not. Or positive semi-definite, exactly. Is that clear? Okay. Let's go back. Why is that? Okay. Now let's look at the geometric interpretation of V dot. So now, if I give you V, okay, and again, examples in the homework and in the assignment, inshallah. If I give you some V, you can check whether it's positive definite or not. I give you, if you calculate the corresponding V dot, and then you can check again with the same technique whether it's positive definite or negative semi-definite and so on. The question is now, how do you calculate the V dot in the first place? Now let's look at, again, let's go to the board and write this down. Let's look at how do we calculate the V dot. But before saying how do we calculate V dot, let's look at what the geometric interpretation of V dot is. What do we mean, first of all, by V dot? The V itself was a function that would take a point in X and give you a value in R. when we looked at X to be Rn, we know what this looks like, but in general, we can have a manifold, and then we have this equation. What about the V dot? So the d by dt of V of X. First of all, where does the time come in place? Where's the time here?
States depend on time.
The state, exactly, they depend on time. So again, so this function of V, so this is not any, we have actually x dot of t is equal to f of x of t. So don't forget that x here is a function of time. Okay, so this is our manifold that we're looking at. The x here is a point, but we're thinking about trajectories of the system. So this is x of t starting from some x of 0. So these are the trajectories of the system in the state space. So the v dot as a function of x is nothing else than actually the time derivative of this function along the trajectories of the system. Okay, so you see, because we're talking about along trajectories of the system, the v dot will involve the x dot in some case. Okay, and again, to remind you, if x was a point on the manifold, or x of t is a curve on the manifold, what was x dot? So x dot at any point in time, what was it? It was a vector, exactly, at the point x of t to the manifold x. Okay, so keep that in mind. How do we calculate this one? Again, let's do the easy case. Let's think of Rn first. So let's think of this to be Rn. How do we calculate the time derivative of a function of Rn? You take the gradient, exactly. You take the gradient, which we called it as the Jacobian of the function v, right? Evaluated at x of t, and then you multiply it by what? By x dot, exactly. Okay. You might have seen this equation in a different way. You might have seen it, okay, let me write this. This is not the Jacobian here. Should just be the gradient. I think we called it dv last time. I think I called it dv in a previous lecture. Can anyone confirm just what was the notation we used? 1 second. Go back. Sorry?
Jacobian, then you convert the x to the critical point.
No, there is no Jacobian here. No. The Jacobian, actually, when we defined it as a multiple. We looked at f1 and f2 up to fn, and then we had like a concatenation of all of these differentials. Okay, let me just recall how we introduced it. I think it was lecture 17. Or was it? Yeah, exactly. We called it dv of x. And again, to remind you, we said that if I have a function that goes from Rn to R, then we call the df of x was equal to partial f by partial x1 up to partial f by partial xn. Okay, and all of these were a function of x. Okay, so this is just a reminder of the df. And here we're looking at the function v. So the dv as x of t multiplied by x dot of t. And again, you probably have seen this in another way, maybe in another notation. You probably have seen this as v dot is equal to partial v by partial x transpose multiplied by x dot. Have anyone seen this before? Yeah. This is very ugly notation, very bad. Why is that? Because it says that x dot is an Rn, and partial v by partial x is an Rn, and I can take the transpose of something in Rn multiplied by something in Rn, right? You're comfortable with that. But this tells you more. right? Because this tells you that this is a vector. So again, if we generalize the case where we're looking at a manifold now, the geometric way, then this is a vector. What about this? This is something that will eat the vector and give you in the end a scalar. What did we call that? We called it a covector, okay? And when we look at the covector in Rn, what do we get? We get the row vector. So when we have a row vector and you can multiply it directly by a vector, it acts as a scalar function. But in general, if x is not, okay, so if x is Rn, then this will be a row vector. So this will be 1 by n, and this will be and this will be Rn by 1. This is only if x lives in Rn. But in general, I need a way of combining covectors and vectors. I need a way to combine covectors and vectors. And we introduced it in lecture 4 or 5, very early. So everyone forgot about it, of course. So I'm going to repeat it, that we said that if I have an element of a vector space V, and a tangent space is a vector space, right? And the cotangent space where the covector lives is the dual vector space. So if I have an element V that lives in capital V as a vector space, and I have an element alpha that lives in the dual space, how did we combine both of them? We introduced this notation. We said that there's something called the duality product. There's something called the duality product between a covector and a vector. And if we have multiple spaces, we can just put here that this is where we want to emphasize that this lives on. This is a vector space V. And this is actually a scalar. No, this is just a scalar. And how did we define this scalar? Simply by letting the covector eat the vector. And this is well defined. This is a well-defined notation, right? Because alpha itself is a map that eats a V and goes to R, right? We said that a vector, a covector, is a map that can eat a vector and give you a scalar number. So this is just an extra notation. So in the case, this is only if we have that x lives in Rn. The general case, the geometric picture, we have that this is actually a pairing between the covector dv x of t multiplied or paired with x dot t, which is again, how is it defined? It's defined as dv of x of t, again, dv of x of t. All of this is a map. Sorry, all of this is a covector, which is a map, and it can eat the x dot of t. But we already know that the x dot of t is equal to what? Is equal to f of x and t. Again, let's now remove the time. So because the time, we're going to make it implicit just to make this easy. So and we have this picture. Okay. It's a mouthful, but it's precisely what's going on. Captures exactly the correct nature of Vdot. Now, this expression, okay, people give it a name because it's very famous and it appears a lot. And it appears in many situations, and it's very fundamental in differential geometry. This is actually known as, again, remember f? What was f? What did f of x define on the manifold? No, a vector field, exactly. It defined a vector field that we called it sigma f. So this is a vector field. So if you tell me f, I can tell you the vector field direct, right? They're one-to-one. Now, this expression is known as the Lie derivative of the function v along the vector field sigma f. This is a well-defined thing, okay? It's a vector field, okay? And so this is the Lie derivative of a function. And of course, in the end, we evaluate it at x. Okay. So the conclusion, so here you see V dot as a function of x in the end is given by this thing as a function of x. So the conclusion that I want you to get out of this, that V dot is seen as a function that takes x and goes to R, sees as a function on the manifold, and this V dot geometrically is defined as the Lie derivative of the function V along sigma F. Okay. This is the geometric definition of it. Okay. Is that clear? This is just a side note. This is very important if we want to calculate the V dot or the gradient of something along something that lives on a manifold. Now let's look at the most important thing, which is for our case. I'm going to tell you this is just a motivation so that you don't think that this is completely in the sky and it's not useful. This is just where we're going to be using it next time, inshallah, next lecture, but just to give you a glimpse for now. If I have a Lyapunov function that goes from SO3 to R. So I want to define a Lyapunov function to try to study the stability of rotation matrices. Okay. Then V dot is equal to, let's try it the old way, the way that you're used to. You might say, okay, V dot is partial V by partial R, right? And then you take this to be transposed, multiplied by R dot, right? If you do it with the tools that you already know, you get this result in the end. Does it make any sense? This is completely rubbish. Doesn't make any sense, okay? How do you take the gradient with respect to a function? Sorry, how do you take the gradient of a function with respect to a matrix? Right? But if you look at it from the geometric perspective, if I would like to calculate the gradient of V with respect to R, or in other words, D of V as a function of R, this is defined because this is a covector to R at SO3. While R dot, which you already know about very well, is a tangent vector that lives in this tangent space. So if I have these two guys, and I know how to pair them, and this is the thing we're going to be looking at next time, inshallah, how to pair these two things, I can calculate V dot, okay, that will allow me to study the stability of something that lives on R. Why is this useful? We're going to be using this idea to study not only the stability of a system that lives on rotation matrix, but also to design a controller that will take one orientation to the other. Okay, and we're going to be looking at a PD controller that would take some orientation and bring you to another orientation. Okay, the only way that you were able to do it so far is by taking Euler angles, by taking your actual Euler angles minus the desired Euler angles, multiply them by some PD, some proportional and derivative controller, and you get the result. Okay? But again, this is all working in charts. This will be the geometric way of doing it. All of this is for next time. Okay, I just want to show you why this is important. Okay, by give you an example where X here is SO3. Okay, and this is assuming if we treat SO3 is equal to R3, just completely wrong. Okay.
This was the integration only work when we have a space and it's like covector as such a case.
You always have that. You always have that when you're calculating the V dot. Is that your question? Yes.
Second case, it is the same of the code. I mean, TRSO3 and it's dual.
Yeah.
I mean, the integration, if we have the same two, one and it's dual, will be different.
And what do you mean by integration here?
said how we will, like what we did with the L.
Yep.
We said we will do it next time. I mean, is this a special case because we have a thing and it's dual, or
We always have that. If you go back here, you see this one is always the covector, and this is the vector. So this, you see here, written in this way, lives in R1 times n. Written in that way, in general, this will live in the tangent space, the cotangent space to x at x of t, while this will live in the tangent space of x. You agree? So you're familiar that x dot lives in this space. So whatever will be paired with it will be in the dual. And if I know how to pair them together, okay, I can calculate the V dot. So again, everything we talked about here is how do we calculate the V dot? Of course, in practice, usually we're not going to see all of that unless you have a very complicated example, because usually we work in charts. When we go to the case of SO3, we don't use charts, right? So we have to work on SO3 directly, and this is why this is one of the things will be very important. Later on, I'm going to even show you, I hope we're going to have the time to do it even on SE3. To develop a controller on SE3 that you can actually implement this directly. Implement a geometrically nonlinear controller on SE3 directly. And if you have that, you can control any system that lives on SE3. Does anyone have something that lives in SE3 as a manifold in mind? Any actual system? Drones, exactly. So drones have SE3 as their configuration manifold. And if I know how to derive the Lyapunov functions or do Lyapunov-based control on SO3 or SE3, I can design controllers, geometric controllers for drones. This is for next time, inshallah. We still have some time left. So again, this is not the end. So the next item on our agenda was to try to use Lyapunov's direct method for an example. And again, let's look at some trivial example. Let's go back to the satellite example. So let's go back. Let's try to prove, all right, let's try to do Lyapunov direct method and to try to show the stability of the satellite. We said that the satellite had 4 equilibrium points. One of them, we know it was unstable, so it's out of the, we're not going to be focusing on it. We had one which is the origin. So the first one that we had for the satellite, so omega dot was equal to C1, C2, C3, omega 2, 3, omega 1, 3, and omega 1, 2. So this system had one of the equilibrium points at 0 and 0 and 0. Let's try to start with Lyapunov and try to prove that this method, this function, this equilibrium point is stable. Did we get anything about this equilibrium point using Lyapunov's indirect method? Why? All the eigenvalues were 0, so the method was inconclusive. Let's see if we can get something extra with Lyapunov's direct method. Which Lyapunov function would you like to choose? From what we discussed, choose any quadratic function as a starting point because it will make your life easy. A quadratic function, by just looking at it, I can immediately find out whether it's positive definite or not. So the quadratic function we're going to be using looks something like this. What does this remind you of? Kinetic energy of the system, right? So again, that's why choosing a Lyapunov function, which is the kinetic energy, is very natural. Kinetic energy is always positive. There is no such thing as negative energy, neither kinetic or even potential. There's no such thing as negative energy in general. So if I always choose the energy, I always have something that's positive. If I have the kinetic energy, it's always a quadratic function. Kinetic energy is always quadratic. Even if I had, again, for example, in SE3, we had the twist multiplied by the generalized inertia tensor multiplied by V, and there was a half here, right? This is also quadratic in R6. So we always have this quadratic form. Let's forget about this one. So this is our Lyapunov function. Do we know that J, so what is the condition that V is positive definite? J should have positive eigenvalues. Do we know that J has positive eigenvalues? How? It's an inertia matrix, right? Or inertia tensor. It always has positive eigenvalues because these are the inertias. You can never have negative inertia values along the principal axis because this implies that it's equivalent to have negative mass, and there's no such thing as negative mass. So this is our Lyapunov function. What about the V dot? Again, the V dot, how do you calculate it? The V dot is another function of omega. We said that we're going to be calculating it. In this case, this is R3. So omega here is in R3. So we're not going to look at this Lie derivative stuff, but it's equivalent to it. So we have that this is d of V as a function of omega multiplied by omega dot. This one is equal to partial V by partial omega 1, partial V by partial omega 2, as a function of omega, of course. Omega multiplied by omega dot. Without looking at the individual components, can you just look at this quadratic form and tell me what the dV is? J omega, exactly. So it's J omega transpose. Okay, it's J omega transpose. Here J was a diagonal matrix, so J is equal to J transpose. And also because it's a matrix that has positive, it's a matrix that has positive eigenvalues, which is a positive definite matrix. If you go back a couple of slides to when we discussed about the positive definite matrices, we said that they are always symmetric. Right? So by just whenever you have here a quadratic form of some function and you want to check the positive definiteness, you always have symmetry, okay, implied. So this is a positive, so J and J transpose are equal. So this is multiplied by W dot. This is omega dot. Again, you have two ways of doing it. You can either plug in, this is a 3 by 3 matrix. This is a 3 by 1 vector, and this is this function there. Write it down and see whether you're going to get terms that cancel out each other or not. And in this case, we're not going to be using the C1 and the C2 and the C3. We have to use the J's. We have to plug them back and work out whether it's 0 or not. Or I'm going to show you something very easy now with the tools that you already learned to show that, to continue from here, okay? Without expanding it in omega 1 and omega 2 and omega 3. Remember that this equation that we have was equal to J omega dot was equal to minus omega cross with J omega. You all agree? This rings a bell? It should. And I can also write it as J omega skew symmetric multiplied by omega without the minus, right? Because I can make, first of all, I can write this as instead of omega wedge product, the cross product with the J omega, I can write it as omega tilde multiplied by J omega. And I can invert the signs. I can invert the order of the skew, the vector product, and then I can make this into a skew symmetric. So this is why J omega dot is equal to. And if you go back to one of the previous slides, this is what is this? What is the J omega equal to? What is physically? What does it represent? Angular momentum, exactly. So this is just a skew symmetric form of the angular momentum covector. Okay. Now let's rewrite this one as omega transpose multiplied by J omega dot. If I take the J omega dot from there, so I have omega transpose multiplied by J omega skew symmetric multiplied by omega. There is a property that you should know by heart, okay? Because again, probably you've seen it somewhere. If you have some, this is a general property. If I have something in Rn, some x in Rn, and I multiply x transpose with J multiplied by x, even if this J is a function of x, but as long as you can show that this is a skew symmetric matrix, there's a property here that says that this is always 0. This is a property. a skew-symmetric matrix, when written in this way, will be always exactly equal to 0. Let's go again, just to give you a glimpse, to remind you of what we just did. When we have something that's equal to 0 as a quadratic form, what is the type of what can we say about the definiteness of the J? Semi-definite. Okay. What about the eigenvalues of J from this equation? What do they have? What are they? They are all 0. All eigenvalues here. Okay. Sorry, not are 0. You have one that is 0, and the two that are complex conjugate of each other. Okay. So this you can prove it for yourself. We don't need this property now, but just look at this X transpose J of X is equal to 0 property and compare it to this guy. What can you say? That V dot is exactly equal to 0. You see, you have two ways. Either expanding this one, right, and having a lot of terms and having this term cancel that term. Who here took the nonlinear course with the doing Lyapunov stability? Have you ever had a couple of pages of calculations and then you just get terms that cancel out with each other? This is all of this canceling out. Okay? And it's completely part of the geometry that's available. So this, you remember, this skew symmetry here is because the omega was part of the Lie algebra, right? And this is actually the dual Lie algebra. So there's a lot of geometry going in there. And this is why the math just tells you that this is equal to 0 in one shot. We don't need to expand it and try to cancel out all terms. Now let's apply Lyapunov's theory. What does this mean? Yes. Well, this is what we're doing. Exactly. This is exactly what we're doing. What does this result from Lyapunov's theory tell us? It tells us now we found a function V. It's positive definite. It's quadratic in omega, which means that V of 0. And by the way, the omega equal to 0 is the equilibrium point we're interested in. Don't forget that. So V evaluated at the origin is equal to 0. This is just a quadratic function in 3 dimensions. When we evaluated V dot, we got that it's equal to 0. What does that mean? It means it's negative semi-definite. It's exactly equal to 0. It's not increasing. It's not increasing. And it's not decreasing, which means that it's always stationary. What can you conclude from Lyapunov's theory with this? The origin is only stable, not asymptotically stable. Because if we want this to be asymptotically stable, this should have been decreasing. Okay? Absolutely. This also makes sense. What was this V? Again, this term here, what was it? Physically, kinetic energy. The rate of change of kinetic energy for a satellite that doesn't have any friction, it's just rotating with itself. What does this imply? It means that the kinetic energy is a conserved quantity. Kinetic energy, the rate of change of kinetic energy is equal to 0, which means that energy is conserved. If you start with some initial kinetic energy, it will always keep on rotating, or it will always stay fixed. It will never, right, dissipate this energy or gain the energy. This makes sense. This is just conservation law, right? Energy is conserved. Energy is neither created nor destroyed, unless you have some external forces or something else. And there are no dissipation forces here, so V dot is equal to 0. And again, if you go back from what we mentioned last time, this is always the problem when we try to use the energy as a Lyapunov function for mechanical systems and thus robotic systems. What is the problem? Is that if I choose energy and I don't have any friction, I will never be able to show that this is asymptotically stable. But at least now we showed that this is stable. So therefore, the equilibrium point we can conclude is a stable equilibrium point. So it's the next best thing compared to what we had from Lyapunov's indirect method. Lyapunov's indirect method said that it cannot say anything about the stability of this equilibrium point. Now at least we can prove that it's stable. Okay. Last time I showed you by solving the system, by doing this experiment of flipping the book or flipping the satellite or giving it some initial nudge, that it is a stable point, okay? Because when we rotated that, actually, I didn't show you that. Because this is the equilibrium point that it's stable, that it's fixed, it's not moving at all. Can we do the same for the equilibrium, for the other equilibrium points? Yes, but it will be more technical and it will be harder. We can also show that the other two are stable, okay? With more involvement. But again, this will be just, will take some time that we can use in something else, okay? Any questions? We haven't answered, okay, so now two things. We haven't said, how can we show if we have something, if we always use the energy and we always get the rate of change of the energy is 0, what can we do? The answer is Barbaret's lemma, okay? Sorry, not Lassalle's invariance principle. This is what we're going to be looking at it next time. But now we have a couple of minutes left. Let's do our first controller, okay? This equilibrium point will not, again, if I give it an initial nudge, and because I proved now it's stable, this means that the satellite will start what? Keep on moving. It will never go back to be fixed. It will never go back to being stopped. Let's very quickly do our first controller here by putting back the torque. Yes. Very good question. We didn't, when we used the Jacobian method, the indirect method of Lyapunov, we had a Jacobian and then we plugged in the equilibrium point and then we looked at the eigenvalues and then we said we can conclude the stability of this. Where in all of these steps did we use the fact that we have an equilibrium point of that? In the first one, exactly. Here, this is the only place where we plugged in that we have the origin, okay? If you plug in here another equilibrium point, for example, like the one which was the capital omega and 0, you plug it in here, you're not gonna get 0. This means that you cannot test the positive definiteness with this Lyapunov function. You cannot test the stability of the other equilibrium points using the same Lyapunov function. You have to choose another one. Now, what I'm gonna do very quickly is that I'm gonna put back the torques. Right? I removed completely the inputs, but we always have, if you remember, we had here a torque, which is equivalent to having here plus tau 1, tau 2, and tau 3, right? Which means that this is equal to this guy plus tau. If I repeat all of these equations, all of these same steps, what is the only thing that will change? I'm gonna get here plus omega transpose tau. And this will be omega transpose tau. Now you have the input as part of the Lyapunov analysis, the stability. Can you think of a controller that you would choose here? So a controller here is, can you think of some sort of tau as some function of omega that we called, I think we called it gamma before. Can you think of some gamma of omega that when you plug it in here, you have that V dot is strictly less than 0, strictly negative definite? What? Exactly. We can choose tau is equal to minus omega, or in general, I can choose minus k multiplied by omega, where k here is a positive definite 3 by 3 matrix. So if I take this equation and I plug it in here, you see that I'm going to get this expression. If I know that k, which is my control gains, these are my controller parameters that I can play with, is a symmetric matrix, okay, that is positive definite, then this is minus omega transpose k omega. What does this give us? Something that's strictly negative definite. And thus, I prove that I have a controller that can stabilize the origin. And this is our first controller. First time we do control in the whole geometric control course. Congratulations. Okay. So this is a damping controller. okay? Or a stabilization controller. So if I have this satellite now, and it starts to move for any reason, and I want to make it always fixed, not move. And I have some control inputs on the satellites, maybe some thrusters or something that will allow it to orient itself. Then by just choosing that tau is equal to minus k omega, I can show here that omega equal to 0 is an equilibrium point. It's an asymptotically stable equilibrium point. Not only that, this is quadratic function that is radially unbounded, and I have this to be negative definite. What is the result that we have here? It is globally asymptotically stable, which means that this system, this satellite, starting from any initial condition, if something very hard comes and hits it and makes it rotate very fast, this simple controller will make sure that it stops eventually. Of course, asymptotically. What does asymptotically mean? It means as time goes to infinity. It means very slowly it will start to come back and stop.
So it is global asymptotically.
Globally asymptotically stable. V is a quadratic function that, again, it goes to infinity as you go away from the equilibrium point. It has only one equilibrium point. Sorry, it has one only critical zero, this Lyapunov function. And that's it.
What was opposite case? I have this satellite and I wanted to move.
That's another lecture. That's another lecture. We need to choose another Lyapunov function and then to stabilize it with again with the same principle. Okay, but no, if you stabilize, if you make sure, if you find another Lyapunov function that has a minimum around the equilibrium point that is rotating, and you show that its corresponding Vdot along the trajectory of the system is negative definite, it means that the trajectories of the system will converge to this spinning case. And it means that I'm going to damp the other directions and I'm going to only rotate in one of them. Okay. I wish that we had some time to do it in this. I plan to do it in this lecture, but again, you see, we're already over time. Okay. So maybe in a future lecture, or maybe in a, I'll see whether how to show it to you. Okay. Maybe give it to you some supplementary stuff that you can read. But for now, this is all what we need. And our first controller. Next time, inshallah, we're going to be looking at more control using the tools that we already learned. Okay. Thank you very much.